Okay, let's get started then. I know it's a cold today, and thanks everyone for coming here. I know it's you're here, not for me, but I'll be happy you're here anyway. So we have been talking about pandas and mostly dealing with structured data. When you have structured data, pandas is the tool you want to use. That's why if I want to spend a bit more time for those of you who are new to Python and new to data science. Pandas is a tool you want to grasp and use, for many years in the future if you want to continue along this path. Today we all switch gear to a different kind of like data we're going to analyze. It's called a graph, or graphs or graph data set, whatever you call it. If you are familiar with social networks or alien networks like that, internet itself could be considered as a graph. Social network is a graph. The disease contagious map or tracing could be considered as a graph. So there are many ways you can use a graph to analyze the data. And the optimal way to save, analyze, and even make predictive models for graph-based data is not the same as the traditional tools we're using, like pandas or Excel, those kind of tools. For those of you who are new to graph analytics, and today's will be the perfect topic for you all. And if you're already familiar with that, it's fine. I think it's good to review some of the materials we already learned. This is a project I worked on like many years ago. I'm not here to show you my project. I'm here to show you how my project evolved in the last, that's actually started in 2013 or 14. I forgot exactly year, but every dot there in this graph shows a new file that committed or some other people committed. So this is a history of the repository that contains all the files that we committed to a code base. That's a software packet. There is an animation here. If you want, you can watch the animation, but I think we can probably give it a try today as well. I cannot maximize it for some reason. But again, you can find you can get to the YouTube link and try it out yourself. So what does is create an animation to keep track of the commitment of every changes I made to a particular file. The structure sounds very complicated. If you are thinking about a version control system, it's trying to keep track of every tiny changes you made to the files and a particular line of files and a particular part of that line. And also it's keep track of all the files. So that's a version control system. GitHub is working this way. Back then we were using a system called a Subversion. And before that, there was a system called a version CVS, concurrent version system, like a CVS, pharmacy store. So this is a way that you can create a graph, and this graph can help you to keep this structure very nicely. This is a tree structure. If you consider, I think I probably start from here. That's the root, where everything got started. It's like a file structure. Starting with the root, you add more files, and gradually grow, and you get your files added gradually. So that's my first, I think, a real life use it. I'm not sure how can I hide this one. Probably I can. And then I have multiple titles here on campus, so I got some privilege to have more than one offices. So one of my offices, actually now I have another one here, and I don't have my office in the Henderson door anymore. That's where the HPRC is located. Now I have one here and architecture building here. So now, back then when I was creating this, I was trying to figure out, what's the walking distance. When I first came to the campus, I used the GPS to go around because I couldn't find where, all the places are. Even a couple of days ago, I have a visitor. When I tried to show her a place at West Camp, I have to use the GPS. It's just like campus is so big, right? I'm not sure how many are still using GPS to walk around the campus. Probably just not myself. Some of you. Okay. So GPS is using the so-called web services. The web services, you can consider it's more or less like a graph. Every location that you are starting from and you want to end to, you go from and to, could be considered as the nodes. And whatever the path you're passing through, actually, it could be considered as the small sections of line segments connecting together. All those could be treated as connected graphs, and connected edges to all your nodes. So edges and nodes put together, you have a graph. So essentially, this problem to find the path for me to go from here to here, it's a shortest path for me to find the shortest path on this graph. Okay, and that's one of very commonly used application for graph as well. And there are very specialized libraries and algorithms for you to find the shortest paths. And we'll have some examples later on today with the Python. And you'll see how, I really like the example, and you'll like it too, and you may find it useful. Now, sometimes I do want to hide this thing, and bottom, top. So this is another graph I created actually today when I just trying to create more relevant examples, because I learned it from you all, and then I think it's probably good to add some more relevant. So this is a disease transmission network. It's generated with random numbers. As you'll see some examples today on how this could be easily generated. If you have some information about this, this disease transmission system, you probably can generate this with the real world data. This is extremely useful when you're talking about, during the pandemic in China, they have been using this kind of system, but it's just more complicated. They need a lot of coordination by the government, by local agencies, but essentially it's a graph. It's a directed graph. You don't only need to know the contact made by two people. You want to know the direction, who carried this, already got, has a disease, carries the virus, and then reach out to the other. So fortunately, we have the contract. If you do the test, on a regular basis, you can have a better control of this. That's exactly what the Chinese government was doing during the pandemic. So at the early stage, it's getting really, really bad. But later on, when everyone, not just the government itself, all the Chinese, my parents, my grandparents, and also my relatives, they all follow the instructions. They just voluntarily they go there and do the regular checking on a daily basis. So the government could have this data that they use to build this kind of model to help them keep track of every single cases, which is quite impressive. Just think about 1.2, 1.4 billion people, right, in China. So this is a graph, and we'll also get into the some analysis about how you can analyze this kind of graph. How do you want to study the centrality, similarity of this kind of graph? We'll get into that a bit later. This is another example, which is not quite look like a graph, but it's very, very relevant. It's actually one of my first examples that I have to get into a graph library to learn how to cut all these pieces. This is a simulation of a concrete ring, two concrete rings. This is using so-called discrete element method, which is much more complicated than a regular finite element method. Probably you heard about people doing this structure simulations. In this case, every single piece could be detached from this system, and you are not creating a continuous mesh. You're creating a discrete meshes. So every time you get a new mesh created, when you want to run this simulation, there's no way you can run it on a single computer. You have to run this on a gigantic supercomputers. Now the very next question you might ask is how to cut this into small pieces so that I can distribute the computational load equally well on each computing node. Okay, to do that, you might say, okay, let's just simply do this count a number of elements and do that. But then there's another question. To maximize the performance of this kind of code to do this simulation, right? You evolve from time t equal to 0, t equal to 1, t equal to 2. Every time you need a synchronization across multiple nodes on your computer. And in that case, you want to minimize the communication cost. The communication cost is linearly dependent, not probably just, I would say correlated, probably not linear dependent, correlated with the surfaces of the cutting. Where you cut it, and if you have a maximum surface somewhere, this surface might require a lot of communication between two connecting nodes, because this part is on processor 1, this part on processor 2. You want to synchronize across the boundary. if the boundary here is pretty big, that means the cost is big. And you want to balance all the surface as well. So it's a global optimization problem when you do this cutting. And it's not simply just counting number of cells, you also consider the surface, contact area between two different nodes. That's a graph problem. Actually the team who did this kind of partitioning is from Minnesota. They got a very, very powerful tool called Partis and Metis, actually. Metis. The parallel version is called Par Metis. It was developed by a mathematician, and it's a very powerful tool in the computational science domain. And that's a graph-based theory. So today we'll dig a little bit into the graph theory a little bit. I'm not expert on graph theory myself. I learned the basics. I understand what's going on, but I didn't get into the theoretical analysis myself. I understand some concept. That's why I'm here, just talk with you about some of the things I learned. But if you want to learn more about graph theory, there are books and books and books. You can read a lot of books on graph theory itself. So essentially, graph is like a pair of, a set of pairs of vertices and edges. That's a mathematical term. There's a counterpart actually used a lot in the networking theory. It's called network theory. It's more like application level. That's when people are working on computer networks. There's computer scientists. Most computer scientists, theoretical computer scientists, are coming from with a very strong mathematical background. So they created a network series. Actually, it turns out mathematically these are almost identical. The way how they develop a series, the way how all the algorithms got developed, they're very similar series. But this is more mathematical. This considers like high-level abstraction on the mathematical term, graph theory. Network theory is kind of like, you might consider it like one of the applications of graph theory in particular area, but fundamentally they are actually the same thing. So when I talk about vertices, edges, and nodes and links, I always interchange them. But nodes and vertices are just representing all the dots in your graph, and where each dot is representing each entity in your graph. Could it be a patient? Could it be an airport? Could it be a machine? Could it be a classroom? That's depending on your application. The link is mostly about communication, linkage, whatever linkage it may have. Could it be a wireless connection? Could it be an airline route, connecting two cities? Could it be a hyperlink between two websites? That's a link. Or could it be called edges? So anyway, so you probably hear me interchange this too, because I learned most of graph theory through doing networking analysis myself. I'll show you some work I did in a second. But the graph theory is more fundamental. I learned those by reading those books. But essentially, it's a combination of pairs of dots and lines, and that's it. Kind of like when someone talk with you about computer science, and on the hardware level, it's complicated. You need to design circuits, figure out how to control the gates, and control the current, voltage, make the oscillators, etc. But on the application level, as long as you build something on top of the digital circuit level, all you need to worry about just 0 and 1s. Just 0 and 1s, nothing more, nothing less. Everything you see electronically is just a combination of 0s and 1s, right? If you have any background in the computer science, that's probably all your teacher telling you. We are just playing around with 0 1s, but how the 0 1s put together could build this complicated virtual environment or digital system, it's quite a miracle. It's the combination of hardworking and also some creative, innovative technology. But fundamentally, it's just 0 and 1s. Now, graph is fundamentally just nodes and links or vertices and edges, and that's it. And for different complex systems, you have different combinations. You put them together, and that's 100% driven by your application. You are the one, if you are doing some analysis, you are the one trying to make this mapping from that particular complicated structure to 0 and 1s, how those edges and the nodes, edges and vertices, how you put them together, how to do this mapping. That's the tricky part. After you get everything ported into this framework with all the edges and nodes and build this graph, you now have a very, very a big collection of tools, mathematical tools you can analyze. So after you analyze this graph, and then you can apply the results back into your application and make some conclusions. Right? Think about this, just like someone has some problem to solve, and they talk to me as a software engineer, for example. I'm just have a freelance company. For example, I don't have a company working on it. If I have a freelance company, just say, okay, I can take a task. You ask me to do something, I can write a program. What I'm trying to do here, actually, essentially, take your problem and map everything into 0 and 1s. And then I deliver the 0 and 1s to you and solve your problem. Does that make sense? So that's what I'm doing as a software engineer if I'm working in a company myself. So graph is kind of like this. The key is how to map your knowledge you understand about certain things to this kind of graphical structure. That's something I cannot tell you because that's your domain and your knowledge. It's sometimes, as I mentioned, it's your creativity. It's your way to do this mapping. But fundamentally, after you get this mapped into the graphs, everything else is just ready. You just do the analysis. I want to make an analogy because every time I talk about this, I have to make an analogy. For example, Einstein, when he first came up with the theory of generativity, it's mostly about space and the materials and how this space is driving the materials is driving the space, right? That's what's in his mind. He was not even thought about finding the so-called differential geometry, which was already there, developed like hundreds of years ago, at least 100 years ago, 150, something like that. By Gaussian and Riemann, all those mathematicians, they're already there. Then his friend Grossman introduced this to him, and he mapped directly to that, and everything got connected. So you actually, when you learn generativity, you have to learn the differential geometry. That's how everything got connected. Another one is about very famous example in physics, because I have background, I know more. Probably there are many other more interesting examples, like the standard model in the high energy physics, and there is some interesting structures people don't understand. And there is a very famous mathematician that introduced so-called the fiber bundle. I don't need to go into details. It's just too many stuff. It's a geometrical object defined in the abstract mathematical sense. It turns out it's really useful for describing phenomena in high energy physics. And Seung Young and many other famous Nobel Prize winners make this connection. They use this fiber bundle to describe certain phenomena in high energy physics. They got a Nobel Prize. So it's mostly about this kind of mapping, right? I mean, mathematicians, when they work on this concept, they don't care about real applications. They're just trying to go all the way they can, mathematically and logically, to find what you can do with all this structure. But for application developers, your task is to figure out this kind of mapping. And unless you want to do both, that's not so many people can do that. There's only couple of them. I know, like the one, Roger Penrose and also Ed Witten. Those are the famous ones can do both. But but anyway, so for graph theory, it started in that's most people are saying it started in like 1730s, when Euler started looking at this very famous 7-bridge problem. So the idea, this problem it started from this I'm not sure who started this problem, but that's a problem. Back then, all the mathematicians they do a lot of games and competition locally. The debate on different who can solve this kind of problems. That's probably, I believe, that's when this problem came up, and they start working on this different mathematics. Whoever wins this, some rich people, will give you a prize, or you bet on who can get the solution. So this came out during that period of time. There's a physical representation for this. So there's a town, you all probably heard about this, called Königsberg. I believe it's now it's taken over by Soviet Union for a while. I'm not sure if someone probably knows the history about this city, but I will not get into that part. So this city it has a couple of rivers running through, and there are 7 bridges connecting different parts of the town. So the question is asking, the mathematician, whoever can solve the problem back then, is to figure out a way to go across the town and go across the bridge and to traverse all the parts of the town just once without double crossing the bridges. So that's the like one stroke kind of problem. When you were kids, probably your parents ask you to just draw in one stroke to see if you can draw certain shapes, something like that. So Euler converted it into a problem by abstracting all the tongue, but each part of the tongue as a node, and the bridge as a link. So this is like mathematical abstraction of this problem. And with some proof, I didn't get into the proof myself, but he claimed that there's no way you can do it because of this particular setup. There's odds and even numbers of nodes and edges involved. So you can look into some Wikipedia pages and others and get into this problem, so why it's working on that one. But the point is not to solve this problem. The point is here, starting from this problem, Euler was thinking that, wait a second, this kind of mathematical problem has nothing to do with distance. So whenever we talk about geometry is about angles, distances, right? You needed to have some gauge there, so some like a ruler, to measure the distance to measure the spatial distance. But here, for this kind of problem, you only worry about the connectivity and sometimes holes, actually. If I have a niece who is currently a PhD at University of Chicago, doing this number series, and she has been just teaching me a lot of advanced mathematical concepts. When I talk with her about topology, he said, hey, this is mostly about counting holes, or maybe, I don't know. So topology and graph theories are all about connectivity information, not about distance. There's no reason for you to know exactly, how far A is connected to B. They just want to know if that's connected to B. That's a major difference from graph theory to traditional geometry and other mathematical theories, and which requires some measurements of distance. Okay. So as far as the network topologies are concerned, this is, if you're familiar with local area network, LAN, this probably comes to you pretty easily for you to understand. Like a tree, it's relatively easy to understand. It's just a tree structure with a root, and then you can start growing all the branches and the leaves, and you can go top down and bottom up. So it's the other direction. Line is the simplest way to get all the nodes and all the nodes connected with all the edges. Then you have a ring. Think about the local area network. When you set up a network with all the cables, let's don't worry about wireless. Wireless is different, but wireless is more that's like a star. You have a router, you have every computer connected to the star. But since for this one, I believe there are multiple routers anyway, so you have routers and your nodes are connected to the router. And then the nodes could, if you move to a different direction, they will be connected to another router. But essentially, it's like a star kind of structure for the wireless signals mostly. Then if you go to ring, when you're working a relatively big lamp, they are concerned about redundancy. Sometimes if there is some disconnection between two nodes, in this case, if it's just a line topology for your local area network, if there's any disconnection or anything happening, some other nodes will be cut off from the network. But this ring structure, even if you get one link disconnected, you can still go around to get connected to the other node here, right? So redundancy is a big concern here. That's also relevant to the density we're talking about. Density is more or less like calculating how many edges in your map relevant to your total nodes, right? So we'll talk about that a bit in a second. This is like one of the extreme cases, probably the extreme cases. This is called a fully connected. So for every node, you can find corresponding edges to all the other nodes. So if you have your computers here, you want to connect to any other node, you have a direct connection, like a dedicated route for you to connect to them, so you don't have any clashes or network conflicts, etc. This will give you maximum redundancy and give you maximum connectivity. But it comes with a cost, right? You don't want to do this in your either if you're not using if you are the wide cables, you're using cables, this will be a big mess in your lab. You don't want to do that. So it's always a trade-off between the cost, efficiency, and all this. That's exactly most of the engineering problem is about efficiency and cost. It's essentially engineering is a optimization with certain constraints. That's what engineering is mostly doing. So these are some examples. I found some examples online, and I just some of the examples are just you can easily come up with. For example, social network is something I already mentioned. You have persons. Almost everyone is on social network one less. Either you're on Facebook or LinkedIn. Even your phone book itself is get you connected. It's a social network. Everyone has a phone nowadays. You must have your contact. You have your parents at least. I believe your brothers, sisters, etc. You are living in this society. You have some connections, more or less. And then these are the key. This is a graph. This is a network. Vertices and edges. Edges more or less like connection. Every connection between you and another person will be considered as edge. It's a virtual edge, but it's edge established. Now things are getting more interesting. When you're getting into a real world, it's not simply about edges and vertices. You're attaching attributes to the vertices and edges. That's when everything gets more complicated and more interesting, actually. Given a person, you can attach a portrait of a person like an image. If you treat the image itself as a data point, it's just one extra attribute to this person. Then this person could be online, offline, and the status, phone numbers, and all the other account information, activities. That all could be attached to this person in your graph as extra attributes. Okay. And the same for the connections. You could be connected with this person because you are relatives. That's bloodline, right? Another person might be just connected with because you are colleagues working, on the same project. You could be co-authors. You could be just friends. That's some other extra attributes you can make the connections. Now, this is the one probably most familiar to all of us as a citation network. We use Google, go to Google Scholars and give you citations, and you can find the people you're working with. Here at Scholars at tamu.edu, we are working on a project. Actually, I'm not sure if it's already there online, but we are trying to figure out collaborations among all the researchers here on campus. So I don't know who your collaborating is externally, but we only worry about all the collaborators internally. So in the future, if, for example, DOR, Division of Research, is trying to find a team to work on a certain project, they can just go directly to that group of people, say, hey, they'll also identify the person who has most connections to lead the project. Does that make sense? This is exactly what the DOR is working on, the VPR's office is working on this. And so on one end, you can look at the people. Another one, you can look on the topics. You search the topics and find who is most influential guy in this circle. Just direct talk to the guy and say, hey, do you want to lead this project? Just, VPR's office will support you and give some support, some planning, funding. You can get things started. Another, of course, everyone, I believe most of you here who is faculty, you probably submit your TPT proposal. That's another way. That's ground up. You submit your TPT and identify the clusters from bottom up, and then they get you connected, and you can work on proposals. So that's how they, how they organize the team to work together to write, proposals, for research enterprise. But a citation, this is something very easy to keep track. For example, I can easily find the authors in the list and then make up connections for all the papers. And the references, it's paper linked to paper, and you can build up, a nice graph based on the references as well. And attributes could be added to each edge. Each connection could be like impact factor for this particular connection. Will this journal has a big impact factor? Does this paper has a big impact factor, etc. Right? Airline networks, airports, these are, can easily visualize this connection, right? Internet is the same. Web, internet, World Wide Web. It's more, this is like not on the knowledge side. It's on the information side. But this is, I'm talking about hardware side. You have internet hardware, you have computing nodes, you have networking devices, you have IP locations, and you have networking connections, you have latency bandwidth. All this could be attached to the edges. So all this could be put together and to do some analysis. You can do all these attributes could contribute to this either as a descriptive item or as a weight. Put a weight on this, you can usually do some quick analysis, and you can do some modeling work on that. So that's part one. It's mostly about basics about graph theory and some fundamental concepts about graph. That's mostly what I know. But if you want to learn more, you need to get into some books. And towards the end of this slide deck, I have a couple key terms. I used to put this in the front, but it turns out might not be very helpful. I just put them in the appendix. So these are some key terms I extracted from some graph theory tutorial and books. You don't need to know all of them, but this concept will be helpful for you to understand some terminology used by mathematicians and people doing all this kind of graph theory study, how they define all these things. One of the most, I think, you can go, the path here. This path, the definition of the path is like it's a progressive definition. It's not like one definition at all. It's depending on the previous definition here. You first define a walk is an alternating sequence of vertices and edges, and then if a walk is a trail, if any edges traverse only at most once, you don't go over the same edge twice when you go from one end to another end. So that's a requirement. Now you go to the path when any vertices can only traverse at most once. So you can only pass the edge and the vertices once when you try to define a path. This path is important because when we try to study the shortest path between two nodes, you need to understand this definition, because you cannot go into the circle. You cannot pass any nodes more than once. You cannot pass any edges more than once. That's basic definition of a path here, in terms of graph theory. But in reality, depending on the different cases, you might have exceptions. But just as far as definition itself is concerned, a path is just a non-repeating connection of you cannot go across the nodes and nodes and edges more than once. That's basically the requirement. But it needed to have an alternating sequence of vertices and edges. You connect them, you get a path. So visually, you can see a path is going forward, but a walk is more a more loosely defined path in a sense. You can go back and forth, and you can go across edge multiple times, go across the same node multiple times. That's still a walk, but it's not defined as a path in this case. So that's probably most important one. The other one I want you all to know is called a degree. Where's the degree at? Okay, degree is, this is also very important. A degree is given a vertex. Degree is a number of edges connecting to this vertex. That's called a degree of the vertex. And for given a graph, every node, every vertex has its own degrees. And with that, as long as you have a degree, you can easily compare them. Some of them have more degrees, some have less degrees. Now, if you map this concept into a social network, now if you ask me, I'll ask you, if consider me and also Donald Trump, both, Elon Musk maybe, I don't want to put myself with the president, but Elon Musk probably okay. If me and Elon Musk in the same social network, who is more likely to have a higher degree? It's no brainer, right? Elon Musk has more connections. There's more lines connecting to him. So in the social network, in this context, the one with a higher degree are the ones that, when you're doing marketing, you are the one who want to spend money on them for them to help you to do the advertisement. Right? When you do the marketing research, you are looking for people with high impact, and that's why this kind of measurements definitely helps. So degree is just one way. There are some other things we'll talk about a bit later. But again, these are some key definitions that you want to get yourself familiar with. And all the graphs, these are all the graphs we are dealing with. We don't have any loops. For example, you don't have vertices to connect back to the vertex itself. You don't have links to connect the vertex back to itself. So there's no loops. So an edge is in the form of the VV. Basically, you have a vertex here. If you have an edge connecting back to itself, it's called a loop. For simple graphs we are dealing with, in most of our cases, we don't have loops. But in some special cases, you can have an edge go back to yourself. This will make your analysis a bit harder, because you cannot use a very general formulation to do this analysis, because there's extra condition inside your graph. But we cannot say this not existing. In some cases, you have to get a loop back to itself. But for simple graphs, there's no loops, And also there is no so-called parallel edges, means you have A and B, two nodes, or two, what is this? Then you have edge 1, edge 2 connected these two. Then you have two parallel edges. This is not allowed for a simple graph. But in reality, it's also possible. If you go from, say, Texas A&M to another place, there are multiple routes there. You have many, many parallel edges, which is definitely, definitely possible. But again, here, in the definition of a simple graph, it has no parallel edges or parallel loops, which is not necessarily representing the realistic cases, but it's usually used for simple analysis, which is sufficient for some quick, quick analysis. Okay. So this is essentially, if you are familiar with all different systems like category series, graph series, group series, they all start with those fundamental definition of all the elemental objects. Like here, you have what is these edges, right? Group theory, you have all the, define a set, you have different elements inside your sets. And then they are defining all kinds of terms with different conditions. Then they finally they define all these special cases, and then they filter out all the special cases and analyze those simple and cases. And then they divide these different cases in different groups and then study them separately. It's almost all the series following this kind of path. It's like a theorem like framework people are using for all this kind of mathematical series. Okay, so I'll not get into the details. If you're interested, go back to that. Let me get into this second part here, graph analytics. Okay. So the Python module that we'll be using today and learn how to use it is called a Network X. And it's very, very powerful. And it can do almost everything I talk about and anything I haven't talked about, a lot of things I haven't talked about. If there's any algorithm you can find in graph theory, you can probably find an implementation inside a Network X, kind of like scikit-learn. Whenever you can find some machine learning series algorithms, you can find some implementation or similar implementations in scikit-learn. That's why it's getting so popular, because everyone's contributing to it. Everyone like it, everyone use it, everyone, when they publish something, they implement a theory and put it into Network X framework, others can easily just use their algorithm directly. That makes your work more impactful, and people can use it to do something directly without relearn everything in your paper. Just follow the same pattern. They can just do things directly with your algorithm, which make it a very, very powerful tool for researchers. Now, a drawback is that Network X is not highly optimized for dealing with large graphs. If you're talking about billions of nodes, etc., it's kind of harder to use networks to do those analysis. Either not well parallelized to run on big machines, or some algorithms, just implementation of algorithms might not be highly optimized. But it doesn't mean it's not working. It's just not working for extremely large graphs. That's it. If you get online, you can find some other modules. There are some graph-based databases. They can process graphs in a more systematic manner. Machine learning models, there are graph neural networks, can deal with graphs and make predictive graphs based on neural network and a combination of graph and neural networks, which is another very hot topic nowadays. People are using a graph neural network to design drugs and predict the molecular operations, just like it's a very powerful tool as well. So essentially, Network X can define all the data structures to hold the graphs and diagram, which is we'll talk about the diagram, the multigram, etc. And then it has many standard graph algorithms already implemented, and it has a network structures and analysis measures that you can easily analyze your graph. It also has tools to generate some classic graphs, like bell graphs and something like this. It's called a bell. It looks like dumbbell. Like a dumbbell. You can create a kite, wheels. Those are some very classical graphs you can use to easily generate with this and play with it. It has a lot of simple graphs like that could be easily generated. And also generating this graph is almost a trivial task. And now you can draw it on the piece of paper. You can easily create them it's simply just define your nodes and edges and how they are connected, and you're done. It's just, I'll show you how to do it. You can try some examples yourself. And also, it's able to generate some random graphs and synthetic networks, and can help you to do some quick analysis of your algorithm, which is quite helpful. I think we still have time. Let's just move on. I think, while you're still waiting here, let's get started. Let's click this open in Calamitry. We'll get started with network X. It's kind of like a tutorial like a pandas, but I won't get into that much details for this one. We are more focusing on the analytics part, and other basic fundamental features. I will not get into those. Just it's kind of different from pandas notebook. Oh, by the way, I updated the pandas notebook. If you go back to the previous one, click it, you can get some. You'll get an updated one. I fixed some of those statements which are not working with a newer version of pandas that Google Calamitry is providing. So, like always, we start by implementing, importing the modules. NX is the alias. Why do you use an alias for network X? It's just NX. You can use NX as a alias for network X. PLT is a plotting tool, and this one is more or less changing the color schemes. It's not essential, but it's make your figures more nicely. So first we create a graph. As I mentioned, do you remember last time I mentioned CRUD? Do you still remember that? CRUD, right? Pandas is has a collection of application programming interfaces for CRUD in different categories: create, read, update, delete. So in many cases, as long as you remember this four, you can always find the corresponding functions in network X about graphs. For example, you can easily create a graph, you can read a graph, you can update graphs and delete graphs, right? That's what we are trying to do here. So first we create a graph. So when I do this, I create a graph with 0 vertices and 0 edges. I'm creating a so-called null, N-U-L-L, null graph. That's actually in the definition. If you look at the appendix, actually there is a null graph there. That means it's a graph with nothing. Sometimes you might say, why do we need to define a graph with nothing? Actually, it's kind of like in the group theory. 0 and 1s are essential in the group theory, because that's important when you do certain operations, like a subtraction. From one element to another element, you get 0, right? 0 is important. When you divide one element to another one, you get 1. The same element, you get 1. That's a very important constant you want to keep in there. The same in the graph. When you do some graph analytics, sometimes you do see this null graph pop up when you do some analytics. You don't want to completely remove this special null graph from your connection, because that's part of the whole set you're dealing with. So if you already learned this set, actually empty set is a very important set. Empty set is always empty set always belongs to any set, and any set should I'm sorry, empty set should be contained in any set. That's what this null graph is about. So next we start adding vertices. So we add node 1. Here I use 1 as a representation. It's basically use 1 as a name for this node. Nothing more, nothing less. It doesn't use this as an index. It just uses 1 as a name for it. So I add this node 1. It's just one node. It's called empty. It's empty graph. When you have one node without any edges, it's called empty graph. Well, null graph is you have nothing. And let me double check, guys. I make sure I'm talking about double check the definition here. Where do I have now? Okay, that's at the bottom here. I'm sorry. So when you have a graph which has 0 edges but only nodes, you have 0 edges. That's empty graph. So when I add one node to my graph, it's just still empty graph. I'm sorry. It's only one is called a trivial. I'm sorry. It's a one special case of empty graph. It's called a trivial graph. It's just one vertices. If it has 0 vertices or 0 edges, it's called a null graph. That's the very first example. So all these terms are good to know, but it's not essential. But it's just helpful for you to see how all these things are defined mathematically. Now the next one, I'm adding nodes from a list. This is how you can create a gigantic graph from a data you have. Consider you have a list of your patients. You can create a graph easily with this, but this will simply add in the nodes. It doesn't add you any connections yet, but you can have a graph already created with a list of patients, a list of your dogs you're carrying, and a list of cats, all the animals you're carrying. You can add it into this graph. Okay. Now when you show it, it just show you 3 nodes, no other edges connecting, because I already added the nodes here, 1, 2, 3. That's it. Now next, what I'll do, I'm going to add edge. It's just as simple as add edge. This is a function, because in Python you have to add an empty space. Empty space usually just with underscore. Basically, add edge is basically add edge. That's exactly what you say in English, right? You add edge. That's it. You get 1, 2 connected. So you have an edge created between 1 and 2. And then here you add multiple edges. This is a list. Look at this list. You have 1, 2, 1, 3, 2, 3. These are 3 edges you're adding. Since I already added 1, 2, so this actual 1, 2, 1 will be ignored because I already have a 1, 2 here. So I don't worry about it. So when I print out all the edges, this is the function you print out all your edges you have. You get 3 edges. Next one, I'll just try to draw my edges, which is here. I'll draw my graph. This is a function, a network X function, that can take your graph G, and show the labels on each node. And this is the size of node you want to have. For example, here you want to have 2,000. Probably make it a little smaller, but not big. Probably 1,000. You can change the size of your node, and also the color could be different color. It could be red, it could be green. Those are all predefined parameters you can change, but it's not a big deal. And then you can change the font size, make it smaller, make it bigger. That's your choice as well. Well, it looks like a trivial, right? Because it's only 3 nodes. Someone give you 1 million nodes, things will be dramatically different. It completely cover up the whole green screen here. So I prefer not to draw that, but that's how you get started. You learn from 1 to 3, and then you go to billions and trillions. So that's how we create a graph. We add nodes and edges will connect all the nodes together and give you connected graph visualization like this. Now we have 1, 2, 3 here. It's simple, connected like a triangle. Now what will happen if I remove node 2? Well, if I remove node 2 here, these 2 edges will not have any ending vertices. They'll be automatically removed from the graph, because the edge 2, 3 depending on node 2. If you remove node 2, these 2 edges will be automatically removed. Again, this is just a rule, right? In this definition, it doesn't mean that it has to be this way, but it's implemented. But I think it's very already run this. So since node 2 is not there anymore, when I rerun this, it gives me some error, but it's fine. So now when I try to show all the edges, only have 1 edge left here. It's 1, 3, because node 2 is gone, and then edge is not there anymore. It's kind of like in Chinese saying, 皮之不从，毛之粘附. I'm not sure how to translate that into English. If you don't have the skin, you don't have hair attached to it anymore. Doesn't make sense. That's a Chinese saying. I don't know if it's a right translation, but it kind of, that's how I intuitively understand it. If you don't have all the nodes there, all the edges or the node attached to it, then it's gone, and you don't have that. So actually make it very straightforward for you to clean up your nodes. When you have certain nodes that remove, don't worry about those edges anymore. It's automatically cleaned up, which is actually very convenient for you, right? And then you have a number of edges, and you can simply just this again is a built-in function. After you get this object-oriented programming, so we have this object G here. that all the methods is automatically built into this. After you define a graph, all the functions will come into you for free. You can do that. Yes, if we are just any edges, it automatically pop up. You don't need to worry about all the nodes. Yes. Yes, exactly. I'll show you later. We'll have some examples like that. So these are some commands very useful for you to do some analytics. If you have a huge graph, you want to see how many edges you have, how many nodes you have. This can give you some more or less like statistics, right? Give you some information. If you want to find the corresponding degree of certain node, just give me the node index, or here I only have 1 and 3, only 2 nodes in 1 edges. That's what I have, nothing more. Then you can remove all the nodes and edges and make it a null graph again by doing clear. That's the delete, CRUD, remember? All these are just read, trying to get information, more like the read functions. And finally, this clear is just delete function, CRUD, CRUD. Always like that. Now, giving you a graph, this is a complete graph. I can create it automatically. That's probably the example you just mentioned. I can call the function called a complete graph and automatically create this graph with 5 nodes. And since it's a complete graph, it's more or less like complete is in the same sense it's equivalent to fully connected graph. So I want all my nodes connected. So you get all the number of edges. So can someone think about the formulation for a fully connected graph? The number of edges actually are fully determined after you give me the number of nodes, right? It's a combination theory, and how some of you probably still remember. Give you n balls. I want you to pick 2. How many pairs you can give me? Like give you 5 unique balls, individually, probably red, blue, different colors. How many pairs, different combination of pairs you may have? It's like a CN2, right? C2N, depending on where you learn. Either you learn from a Russian textbook or US textbook. It's a CN2 or CN. Basically, out of n, you pick up 2. So the formulation is n times n minus 1 divided by 2. That's the formula. If you count, give you 5, let's say 4, make it easy. Let's say 3, 4 easier. You can do 4 here. So how many edges you can count? 1, 2, 3, 4, 5, 6, right? So C42 is 4 times 3 divided by 2. That's 6. So that's the total number of edges you can have. That's a combination, total combination you may have. This doesn't consider any orders. It's simply just combination. Now give you 5, the total possible is just C52, which is 5 times 4 divided by 2, totally give you 10 edges. That's it. So this gives you a maximum density. We'll talk about this quantity called density, that you can get a maximum coverage. Of course, at a cost, because every line means some extra construction for your network or some other thing you need to establish. So, right. So, but that's the theoretical maximum connectivity you may have. Now, there are some other examples, like this is a ring topology. We just as mentioned here. You can see you can start a ring with multiple. It's a lollipop graph, and all these are interesting graphs you can create just for quick testing purpose. This is a simple path with alternating connection of nodes and vertices and links, nodes and links, vertices and edges, with no parallel loops or without loops or parallel edges. So that's a path. And then you have a star, which is a star network. All these are, I have more examples here, but we just. This is a commonly used like a balanced tree. You have it's like 2 levels and 5 nodes per level. If you go from the first, you have 5 nodes on the second level. If you go to the second level or third level, you have 1, 2, 3, 4, 5. So you can continue doing that. Probably let's make it 6. Probably it's a lot. Probably too many. It's a 5. Oh, I'm sorry. It's too big. It's a forgot the power. So can I stop it? Let me stop it. Okay, let's make it 3 or 4. Probably 4 should be fine. So the generation itself doesn't take much time. It's mostly about visualization. It's getting really a lot of work needs to be done on the visualization side. But never mind. It's just an example. So we have all these interesting functions to create this dumbbell. That's one. I'm sorry, barbell and not dumbbell. And you can also create meshes, and this is like a 2D grids, so you can get them connected, in this mesh structure, which is commonly used in numerical computations. But again, here, since you don't have any distance, since it's just mostly about connectivity. This is a hypercube. People are saying this actually the gateway to the 4th dimension. So I don't know. It's mathematicians a lot of mathematicians I know that like this kind of shapes pretty much. They can study hyperstructures into the high dimension by building a hypercubes. Anyway, you have triangle, lattice, whatever. I don't care. So that's all. That's all. Oh, actually, there's couple more here. Just let me run through them so then you can see they're all these are building standard networks, and you can play with. It's just randomly anyway. So I'll go through. So next, I'll show you one example. It's a social network example. It's a very famous example. It started, I think, someone published a paper about studying the connectivity information of a karate club, Zachary Karate Club. So actually, there's a story behind it. I'm not getting into the story, but it's mostly about kind of like like politics. Since in that club there's a coach and there is a president. So it's so I believe there was some fighting between the coach and president, and they are trying to figure out how their coach or president, how well they are connected to their members. Think about this. If you build a graph like this for the political system, it's have a similar idea. But again, it's more complex. There's no easy way to do that. Here in US with all the complexity involved. But for this small club with, I'm not sure, 30, 31, you can easily count how many edges. Let me see. So this one is already built in, so you can directly load this. But in general, the easy way to do it is just load a file. There should be a structure save these nodes and connectivity information. You can load it up. You can save it in a graph, and then you can draw it. This is how the graph look like. Well, I'm not sure which one is the coach, which one is the president. But if you look at this figure, it's relatively easy to tell, right? The coaches and presidents, those are the 2 nodes with maximum connectivity. I'm pretty sure this one could be one. I can show you either this one. I forgot which one has more connectivity information here or here, but they have more connections with other members than many other members. But like me, if I'm going to this kind of club, I just go there to learn. I probably don't interact much with others, but probably I only know my coach well. I probably talk with people standing next to me, or Oh, that's interesting. This is a building. It's more or less like let's see. Let me show you this one. Okay, exactly. Because I prepared this data set just for the patient data set. So you can let me go into this one first. So the nodes are just patients. You can build a node just like a list of dictionary, probably list of key value pairs, more or less like. So here, this is a connection of tuples. This actually, for instance, here represent tuples inside. Basically, it's an immutable list, kind of like that's a tuples in Python. It's, for each one, I have a patient here. This is my name of my node, and the rest are my corresponding corresponding attributes. Okay, attributes to my node. For a patient, I have my age, my symptoms, and my status. So I can have thousands of patients like this. So each one is independent to each other. That's my structure for my nodes. That's what data structure looks like. If you want to build a data structure based on for your data, if you can have some script can generate a similar structure, you can easily save it into this structure and paste it here. You can generate a graph quickly. Now, this is just a node information. Of course, you need edge information. With nodes and edges, you can create a linked. This format is called a link node format. It's a very famous link node format used actually before Network X was even started. It's used to do some network analysis or some other stuff. And so this edges is simply giving you the connection of two nodes. That's it. That's all I need to know. Patient 0, patient 1, and I needed to create edge, and that's it. And the rest is simply just the corresponding attributes to this particular edge. I can use that to do something else, do visualization, do analysis. But all I need to know is actually these are most important parts for my edges, just know which node I'm connecting to. So essentially, I can get rid of everything inside this curved parentheses because those are attributes I'm adding in there. But essentially, I just needed to know the connectivity information to create my graph. Now, getting back to this one, since this is directly loaded from the built-in library, so how they save it, I don't know. It could be in that structure, could be different, but I can dump the data into that structure later on. Okay. So next, this is a very simple connectivity. I don't have much information. I don't have very nice view about what's going on there. So I created this function can draw this more nicely with some other features, with colors, etc. Let's just get in there. Not sure if I can show it. Why not showing here? This is my fingers. Where's my other one? Which one is this? Oh, this is a Kratikon. So this is my draw function. I just draw this one with all the labels. Now you can easily see now it seems 0. It has many connections. If you count the number of lines it's connected to, it has 1, 2, 3, 4, 5, 6, 7, 8, 9. It's many, probably more than 10. And 33 and 32, they also have a lot of connections. So I don't know which one is a code yet, but okay, let me go back to. Let me finish the first part first, and then we'll get into the slides, and then we go back to this one because there are some other concepts might need a little bit introduction. So next, this one I created another example with this edges and nodes explicitly listed here as a list. It's just a collection of edges and a collection of nodes. Okay. Now the interesting part is if I don't have all these nodes, I can still create my graph because when I add edges, the nodes will be added automatically. But I'll be missing all these attributes. So that's why it's important to have also nodes here. Not only adding all the nodes, but make sure you have all the nodes, but also you needed to add all the attributes to your nodes, which cannot be put in here because this only concerned about attributes for the edges. That's a format defined. Okay. So first I created this, and then I add all the nodes from this list. I add all the edges from this. That's what I just showed you all. You can massively add all the edges and nodes from a list. These two are lists. So this will show you some example. Let me draw this. I'm not sure if it'll. So this is like a default visualization, showing you how all the patients are connected. Patient 1, 0, 5, 6, etc. Is how they got contaminated. Okay. And this is by default, it shows the position of the nodes and also the labels, where the labels are located. So this is using the default labels positioning, just centered around the node so you can get that. position actually overlapping with a particular position, center of the node. This is like more a nice figure, and also trying to use the color to representing if it's recovered, if it's still sick, because we have some generated information here, status. Okay, status, you can use the status to change the color. If it's active, it's you can use a different color. If here, that's the if the node status recovered, if it's it will be green if the node status is recovered, else it's red. We only have two status. Otherwise, you can have another statement. So then you can plot out the green or red in your figure. So then you can easily see if it's recovered or not. So that's giving you another layer of information. Color itself is very helpful. It gives you a certain extra dimension of information in your plots. And also the arrow shows you a direction. It's a directed figure, a directed graph. Okay. So to get into the, oh, this is more, I'm sorry, this is more, it's a much bigger transmission graph. This one, I'm not using this list because that will be too big, the file. I don't want to load it file either. So what I did, I just generate this randomly. I have some random numbers. I generate 100 patients as a, with 1 or 0 and 100 as a target. And then I create edges directly. So that's how I generated the figure below. We have 100 patients. And then use the same plotting tool, I plotted out this. It's basically, it's just random generated graph, but it shows you, how things could be done with network X. You already have a non-trivial graph that can help you to understand certain things if you have a real-world data coming like that. Okay, I guess we can continue because I don't want you all to miss the last example, which I think is very, very interesting, and you'll like it. So as far as networks are concerned, there are essentially 3 types, and actually there could be a combination of different types, but essentially you can categorize them into 3 major groups. One of them is so-called undirected edges. That's actually the graph you have been creating, except the patient, the disease transmission graph. That one is a directed graph. All the others we have been playing around is mostly just undirected. You don't worry about the direction from A to B and B to A. As long as they're connected, that's it. The other one is called directed, and more or less like you need to find an arrow to, the direction from A to B or B to C. And that's important because, for example, if you have a one-way road, you can only go from A to B on the road. There's no way you go back because that will be a violation of the traffic, rules, traffic laws. That's a one-way direction. Or if you think about the generation, how to call it, the tree, what's the name? The geology. You have an inheritance tree, more or less like that. Then it's go all the way from your, say, grandparents, parents, all the way to you and your children and your grandchildren, etc. It's just multiple layers, right? That's one direction, going all the way from root all the way to the bottom. That's how you define the directions. It's no way going up. It's historically, and if you consider time as your hidden variable, you're always going forward in time. So that's the direction you're starting. For the weighted trees, that's when you have all the weights and numerical weights. Sometimes nowadays, when you have another model, these weights could be more general because another models can do some analysis based on the connection. It's relying on the graph, knowledge graph, to do something more interesting, but we are not getting there yet. So essentially, when you do some graph analytics, you want to know some numerical quantitative measurements about weights. For example, if you're going from, say, C to G, if you simply measure the distance, C to G might be the longest based on, actually it's roughly, we just imagine from C to G probably longest. But if you're measuring the, the time taken, it might be from A to F, you have a highway, and F to G has a highway. Actually, total time taken from C to G might be shorter. And from A to B, because it's probably country yard road, it's probably harder to drive. The maximum speed is probably 20, 30. You won't be able to go that far. So the total time taken for you to from C to B will be actually longer. If you drive on Google Maps will ask you to see if you want to optimize for distance or time or even gasoline, right? It's greenness. So it's based on the weights. It's calculating the optimal route for you based on the weights you put in there. You are providing extra information for each edges, and then the total calculation will be different. So that's when you combine your connectivity with certain weights you apply on individual edges. That's have a weighted graph. Of course, you may easily combine weighted undirected. This is weighted undirected. You have a weighted directed graph. That's also possible. So that's very general. When you're applying the graph analytics into the real world scenario, this is the most common case because almost all the edges contain some weights, and you need to consider them to make analysis really reasonable. Otherwise, it's just theoretical analysis. You need some connection with the real world. Sorry, there are some questions. Now we know this, graphically we have very nice very nice description and representation about the graph. But mathematically, when you're dealing with all this connectivity information, to store this information into some mathematical structure and do some manipulation about those, you use matrices. Again, matrices now is like dominating. When you learn in machine learning, you use the matrices. You work on quantum mechanics using matrices. It's even called matrix mechanics many years ago. And matrix is a very, very powerful mathematical tool for you to do a lot of interesting stuff. The so-called adjacency matrices is simply the matrix constructed based on the connectivity information along your column and the rows. You try to, whenever there's a connection, you just need to put a 1 there for this non-weighted. If you have weights, you definitely put a weights there. But for the just undirected, no weights graph, weightless graph, you just put the 1 there, representing there is a connection between A and B. Okay. Now, for this simple graph, we don't have any loops or parallel edges. So it doesn't have a connection to A itself because there is no loop. If you have a loop, we just put A here. This diagonal term, the first diagonal term should be 1 if there is a loop connecting A to itself. But we don't have that. So we simply just put all the zeros along the diagonal term. Those are because we don't have loops. That's straightforward. Now, if you do a quick summation of all the rows, all the row items, you can easily calculate the corresponding degrees. More or less like, because when A is connected to B, you have a 1 there. Connected to C, you have a 1 there. If you sum up all the row columns, all the row items, you get 5. But again, because this undirected graph is a symmetric, you calculate all the sum, or you sum up all the elements along this column, you also get 5 because it's symmetric. So it doesn't really matter for undirected graph. Now, if you are talking about a directed graph, it's a little bit different. When A is connected to B, means usually, when we say A connected to B, we go from row to column. So A is connected to B, then there is a 1 here. But when there's no B goes to A because it's a directed graph, so you get a 0. So for this directed, the graph, the representation is just upper triangular matrix or lower triangle, depending on how you define. If A, how you define this 1, where the 1 should be set, either B to A or A to B. But that's after you have a definition. Say go from column to go from row to column, you set this 1, then you'll have upper matrix. Otherwise, it will be lower matrix. In either case, it's not symmetric anymore because you have a preferred direction. Okay, in your matrix. But when you sum up all the elements together, you also get the corresponding values along this column direction. You have outgoing degrees as well. So how to count the ingoing out degree and the in degree? You can just count all the columns along this direction. You get, say B, there is a 1 incoming degree. C has 1. If you do you sum up all the connections here, you get a corresponding in degree. So in degree, out degrees are different because one of them is coming in and other going out, right? Now the weighted degree, since this one is also is not directed, undirected, so it should be symmetrical matrix, and the corresponding corresponding value will not be simply the 1 anymore. It will be a scalar multiplied by 1. It's simply just, you can put the weight there. For A and B, you have 8, and C, you have 12, etc. You just put everything. And you can measure corresponding degrees based on the weights, which is, also makes more sense because this degree also, depending on the connection, more connections or more important connections will contribute more to your degree, which also makes sense, as far as definition of degree is concerned. So these are 3 matrices that you can use to 3 different matrices for different graphs you can use to do some analysis. Okay. Now, after you map this graph into matrices, matrices has its own system of manipulation that you can play with. You can study the eigenvalues, you can study eigenvectors, there are many other things. People are talking about how you do the spectral analysis with matrix, etc. There's a whole bunch of tools developed for matrix could be applied here as well. So that's getting things more interesting. Now you have a graph, a lot of mathematical tools developed for graphs. If you have a mathematical representation as a matrix representing this graph, then you have a whole set of mathematical tools developed for matrix could be applied to this as well. So you have different ways to analyze this this graph, either through matrix toolbox or through the graph toolbox, which is quite impressive. Sometimes you may find some interesting connections between some of those. Just for example, this is a very simple example. I have my adjacent matrix established. This is a undirected graph. This is intuitive. Everyone can understand what I'm doing here. As long as you know what a matrix multiplication is. I have connectivity, this adjacent matrix constructed. I simply take the power of this matrix. Nothing more. I just take power, more or less like a matrix multiply matrix. Column times the rows, this column times this row, dot this row, and it gets the first value. You got 5, etc. After all this operation, after multiplying these matrices, actually, if you look at the diagonal, did I close the light? Turn off the light? Yeah, no one's moving, it's automatically turned off. So if you do that, if you look at the diagonal signal, actually this diagonal axis contains the degree of A. It's kind of like you have A have 5 loops to A itself. In some sense, this M power gives you the degree of the corresponding nodes in your diagonal axis. There are some other operations for this matrix, and you can look up some references. But this is just one example I find it's kind of interesting. If you just simply do the power, this could be done. Of course, you can also do the summation and get the corresponding degrees. But I didn't expect you can get to these values, in this way. But it just happens. It's kind of interesting to see how things are working. So there are a whole system of matrix manipulation could be applied to this analysis using this adjacent matrix as well. Let's see. Okay. So I talk about the average path length. Probably I haven't talked about this part yet, but this is a measurement of the connectivity information given a graph, given arbitrary pair of nodes inside the graph. You want to measure the shortest path between them to see how many jumps you're going from, say, A to B. If you have 2 edges connecting, connecting all the 3 nodes together, but the starting nodes and ending nodes, you have 2 edges. That's a number 2. So this D will be 2 for that particular pair. You keep doing this counting and trying to calculate all the possible shortest paths between all the nodes. You sum them up. As long as, since we don't have loops, so this I will never equal to J because you don't have point, the node A going to node A, you only have node A going to B, C, D, etc. So you do this shortest path, find out the shortest path to go from A to all the other nodes. You sum them up. It's just simply just a numerical, integer number, natural numbers. You sum them up and divided by this normalization factor. This is this is something I already talked about. When you have what's the maximum time given a number of nodes, the maximum possible edges is n times n minus 1 divided by 2. So this LG is more or less like normalized by the maximum number of nodes. If you multiply, you divide both the top and the bottom by 2, this is the total number of edges you may have. This is the total total distance between all the possible pairs. And this more or less gives you the measurements of the efficiency of the network. How the information could be easily transferred from A to B if you have a lower, let's see, it's a measure information. So if it measures a step, if it has a large D, that means you needed to go across your network multiple steps to go from point A to point B. For the fully connected graph, let's consider some special case. For the fully connected graph, this is always 1, right? For the fully connected graph. So how many nodes do we have? For 5 nodes, this is always 1. And the total cumulation of this will be n 5 times 5 minus 1 divided by 2. You get this LG will become 1/2. And you can get the roughly this probably the maximum value for this LG. There should be a 2 somewhere because this should be normalized to 1, but I'll check the formula. But this is basically how you calculate the efficiency for transmission of energy transmission of information. You want the minimum distance to go for your network. This one is just opposite. The same normalization factor, but this part is just the inverse of D. This is more or less measuring efficiency. We want this one to be small so that this EG should be maximized. More or less like it's the inverse of the previous, even though it's not mathematically inverse, but it's more or less like the inverse of the distance. So it's measure the efficiency of network. For example, if you have a network about government agencies, you can measure how much time for some information or some documents go from A to B. Then you can estimate, give a number about the whole structure. Musk mentioned about the retirement. I'm not sure you guys watched the video. Musk and Donald Trump a couple of days ago, they kind of Donald Trump is carrying his child. I'm sure, did you watch that one? It's a half-an-hour video. He was talking about how his team is working on the efficiency. He mentioned about a very specific example about a retirement in the federal government, because all the documents. I listened to that carefully. That's why I still remember that very interesting example. All the government retirement documents has to be physical copies. They have to go to a very special place to archive those, and all the documents have to go through a very specific elevator. And the maximum number of retirements you can handle is highly dependent on how fast this elevator is moving. Does it make sense? So that's how the government is working. So that's based on, again, it's based on Musk description, but you can check the facts. I don't know, but it's kind of interesting thing. That's exactly what we're trying to do here. If you think about the efficiency, there's the efficiency actually is if you measure this one, it's actually efficiency is dramatically decreased for any small numbers like this. It will gradually, big numbers. This will dramatically decrease the efficiency for the whole system. So the bottleneck in the government system, that as Elon Musk described, that's what I perceived from that 30 minutes, about 30 minutes video. It's Fox News has that, or Fox or Bloomberg News. I forgot which news. They posted on YouTube. You can search that. It's just 30 minutes. It's a very interesting news release, kind of announcement about how this dollar system is working, right? And that's one example. That actually, I think if you think you can build some graphs for all the government agencies and try to model that and model the transmission of information through different agencies based on the time taken for one piece of information go to another piece, another department. You can build up network. And this could be used to easily measure the efficiency from different scenarios, right? So when I was hearing him talking about the efficiency for that particular retirement process, I thought about this formula, and actually it's a kind of interesting connection. Being able to traverse the, I believe it's the right pronunciation, traverse the network. This is a very important thing that people want to do. That when someone give you a graph, you want to visit all the possible nodes in the shortest path. That's a different way of doing the so-called graph traversal. To traverse this total graph will take you some time. If you visit in IKEA, the way how they design their floors is just make sure you go as long as you can and see all the exhibitions, right? All the furnitures and all the stuff they sell. So the way they design it is like very complicated tree structure. You have to go through all the items, maximize your travel, in the area. But anyway, so there are multiple ways to do this, like a graph traversal, and also Network X has some tools. There are multiple methods to make sure that you go through all these nodes inside of your graph without double crossing all the edges. But sometimes you probably have to, but because depending on the number of edges and number of nodes you have, that's kind of like extended version of the 7-bridge problem. There was always some cases that you have to go across multiple times, but that's not a problem, because for us, all we want to do is want to traverse all the nodes, and we don't have the constraints about have to do that across the edges just once. So there are multiple ways to do it. One of them is called a random search. You start from one place and randomly move to another direction, and if you ended it, that's fine. You mark it down and go to another one. So randomly going to different directions, that's one way to do it. Another one is so-called a depth-first search. You get into one node and you go all the way possible to the maximum levels as much as you can, and then you start from the bottom level up gradually to the first level. And then another one is just clean up all the possible ways. For example, this is your root level. You want to go to the first one. You don't want to go next to the second one. You go back to this one, go back to G. If you finish all the possible levels around this G, this is a 0th level. B and G are first level. A, D, I are the 3rd level, something like that. So you want to finish all your 7 levels before you go to the next one. So that's called a breadth first, and then you finish all your 7 level elements. So there are multiple strategies to go across your nodes like that. Another very commonly used analysis for graphs is so-called centrality. Already talk about degree centrality. For example, if you have a graph social network, when the marketing firm trying to find someone to invest money to help enterprise, say, Coke, right? So what does that do? They go to probably Donald Trump is drinking Coke on a daily basis. If he's willing to take money, I think Coca-Cola will be more than happy to just give him some money for him to advertise for Coca-Cola. But again, for the regular product, all the marketing companies are looking for those nodes in the social network with a maximum synchronity, be it the degree synchronity or between synchronity. Each one has a different definition, but degree synchronity is probably easiest to understand, because if you have a maximum connection, if like I have 1 billion people following me, anything I do, 1 billion people will know right away. And that's no brainer for someone just to invest money for you to advertise for the product, right? So that's very easy to understand. But then there's another one. This one is kind of different. It's called a between-list synchronity. This one's a little bit, it's not a very intuitive, but if you think about it, between-list synchronity are the nodes that appeared in the maximum number of shortest paths between arbitrary pair of nodes. Okay. Between synchronity measures the number of times a node appears in the shortest path between 2 arbitrary pair of nodes. So these are the nodes in the social network working very likely as agents or proxies. They are not the one with the highest number of degrees, but they make connections between all the other nodes. So these are the nodes in your graph might be transmitting the disease most, right? That's the between-list synchronization. That's again depending on the particular application you're looking for. Sometimes you're looking for this kind of between-list synchronity nodes. Sometimes you're avoiding them. So closed-list synchronity are the measures the average length of the shortest path from the node to all the other nodes. It's the shortest. So you can calculate the corresponding nodes to all the other nodes, trying to find the shortest path between particular nodes and other nodes, and trying to estimate what's the average length for this distance. And then you measure all this for all the nodes in your graph and find the one with the shortest average path. So that path, that particular node inside the graph has the shortest connection. It doesn't need to be the degree centrality. It doesn't need to be between-list, but it has a shortest connection to all the other nodes. All this might be converted to the single one, might not be. If it's convergent, then these nodes are extremely valuable for marketing, for other things, right? If it's not, you want to study why it's not, why it's sometimes it's just different scenarios. Okay, so there are multiple other possible scenarios. I'll just go there. I believe I should have some examples. Yeah, we have all the definitions here. You can find the corresponding definition on Wikipedia or some other places. So, and Network X can calculate all this directly for you. So that's the beauty about all this definition. Another very important concept is about density. That's more or less measuring how many edges you have, how your nodes are connected, how well your nodes are connected. This density is actually, it's not, I'm not saying it's linearly dependent on the efficiency, but it's highly relevant to efficiency. If you have a direct connection, you have a lot of edges connecting all your nodes, it's very likely you have a high efficiency network, but at some cost, because every edge costs something. It's not free, right? Any edges might be costing something. So it's always a trade-off. But this D simply measures edges. The maximum density is just 1. If you think about it, the maximum number of edges for the fully connected graph, which is an extreme case, is simply just this is just a definition of a degree of all the vertices inside the graph, which is just n in our previous notation. N times n minus 1 divided by 2, that's your maximum. So E divided by this maximum number is just give you a percentage of the total number of edges you may have compared to the total possible edges you may have. That's more or less a measure of the density of the graph. This figure is very easy. I think this formula is very easy to remember, right? That's just a density measuring how connected you are and how many edges your graph has compared to the nodes you have. Sometimes we have nodes spreading around without any edges. Those are called dangling nodes, and those are the ones without any collection information to the rest of the graph. So for graph analytics, it's very useful. As I mentioned, it's for marketing and analytics. If you're working with folks from business schools, they will be working on this on a daily basis, some of them. They want to figure out the best marketing strategies. They are teaching students how to deliver their pitch. And I work with some of the professors that do. That's their job. When they train entrepreneurs for the next generation, they want to show them, how to deliver a pitch, how to attract donors' money, how to get money from investors, how to sell your product, etc. That's what they're learning. And also, social network analysis is very important, and try to figure out those centralities is very important for them. Fraudulence mitigation with the banking transactions, that's whenever you see something unusual happens, you want to, label them and try to figure out, which transaction, more or less like the transaction, more or less like link. When you have an unusual transaction between A and B, probably the amount of money is going sharply to a maximum amount ever happen, or something else happen. You want to pay attention to that. Route planning for maps, already mentioned about cell tower for cellular network. You want to maximize your coverage in the areas while you want to minimize the number of cellular towers available. So that's more or less like a network you're building, depending on how powerful your cellular tower is. Mesh partitioning, and also that's something I mentioned. So I think we have time, right? What time is it? So this example is a very interesting example. I actually come up with this example and start teaching this ever since I teaching this graph analytics to our students. This is so-called 60 degrees of Kevin Bacon. It's like a game where the players challenge each other to arbitrarily choose an actor and then connect them to another actor via a film of both actors have appeared together. You can repeat this process to try to find the shortest path that ultimately leads to the American actor Kevin Bacon. Okay. So, for example, if you and your friends, your people sitting between next to you, attend the same class, and then another student attend the same class with another famous guy, then your number, probably not called Kevin Bacon number, probably that student name's number will be 2, because you have 2 hops to get connected to another student. You can apply the same game to the citation network. That's exactly what we were doing in the example I just mentioned for DOR to figure out, if the people are collaborating, how they're collaborating. Do they form a network? Do they form a cluster? Are they just like a lone wolf, like alpha wolves working all by themselves, or they're just working together as a gang? That's what we were trying to study for the clustering, and we needed to figure out what's going on. But this is a very interesting example, and let's get into this example quickly. I'm sorry, this is a link, but let's open the Jupyter Notebook. This last update in 2023, but I believe that we started this example like 2021, 22, many years ago. Even that's way before the pandemic, but this was last update a bit late. So Kevin Bacon's Bacon number is 0 because it's himself. So you don't have extra layers, extra nodes to connect to. It's just 0, which makes sense. Then what I'm trying to do, I went to this website. There is a guy, when I was looking to this example, when I teach this graph analysis, the first example I think about, I must want to find something interesting and to get people interested in doing this. So I thought about this movie because everyone watches movies, right? One or two, probably a week or 1 or 2 a year. But everyone probably must have watched 1 or 2 movies. So what's these movies. When you have a movie, you have a cast, you have a number of players, actors, actresses playing them. You have people publishing that. You have producers, you have directors, you have companies, you have a year, and you have corresponding other information. So this database connects all the, let me go to this Wikipedia film database. I'm not sure when this was, okay, it's a pretty old one. No one else is updating this database anymore. It's pretty old, but there's an XML file. You can download this. This is the one I used. It's a pity that no one else is updating this database anymore. But this is the file I downloaded. It contains the movies all the way up to, I'm not sure which year, did I say? Probably 2020 or something. If the last updated in 2000, probably 19, 6 years, but last update is 3. Probably 3 years ago, probably 2021 or something like that. Or 22 maybe. So I downloaded it. This is what I'm doing. So don't worry about all the modules here. This I'll simply just downloading this file from this movie text file. I'll show you what this one is, just in case you're curious. This is a raw data I'm using. Okay, let's Control-C, Control-V, and just open it. And this is the file. Okay, can someone tell what kind of format it is? It's a JSON. It's just a standard JSON file with a key value pairs, right? You have curved parentheses. You have key value pairs for each one, and actually each line here. This is the one. Let me go. Where's okay? It's too big. Even for me to select it will take a while, but it's fine. So like each block here is just 1 entry, and it's already now. I'm selecting 2 entries already. So. So that's what the raw data looks like, okay? Now, this is not a graph database. This is not a graph structure. I have to do some converting and create a graph myself. But for this particular example, the nodes are pretty clear to me. I want to have all my actors and actresses as my nodes. And then what's the linkage there? The movies they are playing together, that's a linkage. That's the edge. With that in my mind, I'll start manipulating this file and trying to figure out how to deal with it. Okay, so you must have this clear picture about how, what are your nodes, what are your edges, and then you build things up. So first I get this loaded up, this file loaded up on my pandas. That's why pandas are almost everywhere. For this data structure, I know it's a JSON, but pandas can read it, which is quite impressive. If you look at this file, this is a top five rows here. Okay, let's see what we have. We have the title. I'm not sure anyone watched this movie. It's like 1997. No? We just don't have time to, how many entries we have? I just show you. Do you want to know how many movies we have in this database? A rough guess? Look, this is a number of entries. 164,318 entries. Each entry is one movie. And each movie is about how many hours? 1.5, probably sometimes 2 hours, some even longer. I'm not sure how anyone can watch all these movies, but we do watch, like Blade Runner. This is a pretty famous movie, right? Harrison Ford. How many of you haven't watched this one, Blade Runner? Go watch it. It's pretty cool. And I'm not a movie watcher myself, but I did watch this one. It's very, very good. The Birth of a Nation. It's also probably a pretty famous one. But this is 1915. So I don't know. This is all probably sorted by the first non-trivial. I'm not sure. It's probably A, B, B. Okay, this starting with alphabetical order with a title here. That's our database. Now look at this thing. As I mentioned, I want to build my database with all the nodes as actor and actresses. They're not showing up here, but in this one directly, it's actually showing up in the cast here. Cast here, cast or cast. I have all the actors and actresses inside this list. But the titles is clear. I can easily use this as my link, or each entry as my link. But I needed to parse this part and get everyone singled out and create a parallel each one, because each one of them, arbitrary pair of every cast member in this movie will have a linkage of this movie. That's how I build a graph. So I can create edges between these two and this two and this two and this two. So totally depending on number of actors or actresses I have in this cast, I can create all the corresponding edges. I think about publication. It's the same. This could be the title of the paper. This is just a list of authors. And you can create movies like that. Or you can create, not movies, you can create linkages and a graph like that. The same, you can create producers based on producer, but with produce most of one or two people, it's kind of hard to have find multiple people as a producer. Sometimes you do, but in most cases, it's one person. So it might not be easy to get a graph based on, but build a graph based on this is relatively easy. Okay. Now, this is what I try to find first, because it's just for exploration, EDA, right? I'm not a big fan of Bruce Lee, but I do watch Bruce Lee's movie a lot. When I was young, there's not so many movies available, so I'm not sure how many, a lot. Are they all Bruce Lee's movies or not? Let's pick any actor. Let's is spelling correct? Okay, let me see. 2007, I'm not sure. The Top Gun, Maverick. This is like 2020. I'm not sure. It's latest, not latest, but anyway. And you can see there are some multiple, like a Top Gun here. There's a Top Gun series at the bottom. I don't know why it's showing up this, but it shows as an extra another entry, but it's actually, oh, doesn't matter then. Okay, okay. I based on that, I'm not watching a lot of movies, but I didn't know that. But I did watch Top Gun because it's free on Amazon Prime. One day when I opened it, it just showed up. I said, okay, let's sit down and watch it. And okay, so again, that's a database we have, which is because everyone can make connections, everyone watch movies, so that's a good example for us to see. This is an interesting part. That's how I create this graph. So first I create an empty graph. It's a null graph, not empty. It's a null graph. Just create a container. I want to put all the stuff inside this G. I iterate through each entry, each row. This is how I do the range. So I get into each row of this data frame, which is showing up here in this table. I want to go into each row of this. Okay, let's look at this line because this is very, I'm sorry, I go too far. Now, I take this cast column and try to find all the possible combinations for each two. Let me do this quickly. Cast. If I show this cast, it just shows all the casts here. That's my cast. And for all the 1064 318 rows, that's my cast. Okay. I take the arbitrary row from it. I take the two element from each row, arbitrary two element. I try to find all the possible combinations. This combination is a special tool inside the iteration tools library, which is very, very powerful. It's here. I think it's here. That's the iteration tools can give you the possible combinations of all elements you may have. So what I did, I created all the possible combinations of any two out of the first row of all the actors, actresses, and I create a list based on that. So I save that into my list. So this is just for individual, I'm iterating across all the rows. For each row, I create a list of all the possible combinations of all the actors. Okay, probably better for me to show you this, then you'll see what I'm talking about. Right, let's go to the previous one and just turn this to 1. I'm sorry, I need to define this G first, X first. Okay. So it's undefined, so it doesn't recognize this F. My list. Print, where's my, it's not defined. My list, I'm sorry, why it's capital case. Okay, so you might see that. Does it make sense? So it's trying to find all the possible combinations of arbitrary two actors or actresses inside my cast, and then I create a list. And the next will be easier. You just simply add edges from this list. And you're iterating through all the movies, and you keep adding them. Now, the beauty for this one is, after I add the list to it, I don't worry about edge all the vertices, because the vertices will be automatically covered. If some actors are already added, they'll add the edges there, but the vertices will not be double added. So I don't worry about redundant vertices in this way. Simply by adding all the edges one by one, and then I can create a fully collected graph, or a collected graph, not fully collected. I can create a graph by just simply adding all the edges. Okay. If there is a movie played only by one actor or actress, it's fine, because this combination will return nothing. So it should not be active, because this particular movie there's no way that this actor could be collaborating with others because there's only one actor. If you have more than one, I can find all the possible combinations and pair them up and create edges based on that. Okay. So I get this. Oh, I need to run this one more time because this will take some time. This will take some because we have 164,000 movies, so it's iterating through that. So after that one is done, we get a pretty big graph containing all the informations about all the actors and their corresponding connection. It's done, probably, I'm not sure, probably 10, 20 seconds. Now, next I'll define a back number. This function is trying to find, I take your actor name, for example, Bruce Lee. I'm trying to find the shortest path, which is a function provided by network X, for this graph G between your actor and Kevin Bacon. And that's it. And then I print out the actor name and Bacon number and shortest path and etc. And I'll just define this function, and then I can use this function. Let's find the Bacon number for Bruce Lee. It's a 3, okay? It's good. I think it's trying to print out something. It's a print out all the possible connections because between Bruce Lee and Kevin Bacon, there could be multiple shortest paths between Eddie Albert, and I don't know. I don't know them, but they have been play all kinds of movies together, through different. So Kevin Bacon must be playing a movie with this, guy and Chuck Norris. Bruce Lee plays with Chuck Norris, and then Chuck Norris plays this anchor with Bacon. So that's also 3, right? Shortest path. 4 people. Basically, it's a 3 hops, 3 paths exactly. Exactly. I just only print out 3. Yes, minimum. That's the shortest path between 3. The shortest path you can find. Yeah, definitely. Shortest path is just 3. So I only print out 3. That's inside my function defined previously. That's here. I only print out the shortest path, which is 3. So you can do this for your favorite actors or actresses. So again, think about how powerful this whole notebook is. It can do this for all the other graphs in many different ways. It's just how you map your problem, your database or datasets into this kind of structure. And such things could be done very, very easily. With that, I think that concludes today. And thank you all so much. Okay, we have some questions here. Is there a way to define edge classes? You have a direct connection, shared attributes, etc. So that could be put into the attributes. Could be quantitatively represented with all like weights or other ways when you do the quantitative analysis. Otherwise, I'm sorry, go ahead.
So I understand that you can look at connections like using the attributes, but I guess, excuse me, what I'm trying to understand is rather than a weight, is there a way to assign different types of edges in a way that you can potentially toggle them on and off so that you can explore things in different ways? Or do you have to just have concrete edges and every edge is an edge and every node is a node with no way to further provide some sort of structure to those 2 basic components?
So I say you are talking about dynamically changing the properties, or for example, it could use some flags inside like attributes. You can write some script, but depending on the flag of the attributes, then you can turn it on and off. You can remove it, you can insert it, you can do this dynamically. Because if you can control individual nodes and edges, right? You can do anything you can with this graph, as long as the graph is under your control with this network X structure. and you can either depending on your condition, you can define those operations as a separate function. Whenever this particular flag is triggered, you can do something about it. So then you need to write a probably separate function to deal with that. But it's not a built-in structure. The structure itself is mostly for holding this information. The operation about this actually highly depending on the application you're working on, and that's your part of a code to control how to turn on and off certain nodes, which is actually directly doable.
Okay, because I'm just thinking in terms of practicality for finding the shortest path.
Yes.
It's when you're mining data and trying to find potential connections, there may be multiple different edge structures that you could be interested in, but you don't necessarily want all of those stored all the time. And so
Yes.
I imagine it can get quite complicated in terms of trying to realize all those connections manually. So I'm trying to think of also, are there ways to mine for potential edge creations?
That's interesting. That's exactly what we were doing when we were working on a different project for protein genome analysis using graphs. So what we were doing, we are getting a subgraph from the big gigantic graph we created. Based on the criteria we put in there, we filter out all the nodes and edges. Those are not satisfying our particular condition. So we can create a subgraph based on the graph we created, and then we analyze using the subgraph itself. So it will be much more efficient.
Interesting. And I think the other potential value and future of this is we don't know what we don't know.
Exactly.
So
yes.
how do you, it seems like this is a really powerful tool, and maybe it's already there, but or I don't know, maybe whether it exists or not, but how to seek out those connections that I don't know. I'm thinking like gaps in knowledge.
To be honest, what you are saying here is exactly the problem we are facing for some of the projects. One of the immediate connection I can make is that for the data analytics we are doing with the current data, we only limited to the data we have access to. We don't know what we don't know, as you said. But now there are a couple of projects ongoing, not my team, and working with a professor from ECE, Electrical Computer Engineering and Computer Science. So they are trying to create generative models, can generate all those nodes and vertices, or nodes and edges that can extend our current graph and extend it to the area or connections that we never know in our data set.
Yes.
And then we can create some filtering mechanism by removing those non-physical, non-realistic nodes from the graph. Then we can go back to study those, which I think it's a good way to use current data and use it combined with the generative AI models.
Yes.
Creative graphs that you can explore furthermore without worrying about missing any data or particular part of the graph that you never know, right?
Right. Oh, I'd love to talk to you more about this at some point.
We have this Bring Your Own Data consultancy workshop. If you go to Tommy's website, you can feel free to sign up a time slot. We'll bring some experts. We can talk with you about this.
Okay, I love it. I'll reach out to you in an email too to get some more information specifically. Thank you for answering that. This is very interesting and exciting.
Sure. Thank you.
Thanks.
Bye-bye.
Bye.
Do you have any other questions? Okay, if not, that's all for today. Thank you all so much. Talk with you all tomorrow. Bye-bye.